So my name is Theofilos Manitaras, and I will today work with you during this morning for Numba, the CPU part, and also for Cython. And we can start with Numba. You saw some things yesterday, but today we are going to look into it in much more detail. So please go connect to the Jupyter Notebook, and you can update your Python HPC as follows. You can git pull so that you take the latest version. And then from the Python HPC folder on your left, you should see the Numba part, not the Numba CUDA, this is for tomorrow. The Numba part, the simple was what you saw yesterday, and Numba CPU and Numba CPU here. So let me put it a little bit on the left. So is the size fine, Tim?
And maybe we can ask the attendees.
Yeah, so.
Yeah, so it looks like it's okay.
Yeah.
If someone can't read it, please speak up and we can make the size a little bit larger.
Yeah, please unmute because for some reason my client is not working properly and I cannot see the Q&A. So I guess we're fine to go. So yesterday you saw a little bit of the basic idea of Numba. So Numba, as you said, is a JIT, just-in-time compiler, which means that as soon as you make some decision and you want to compile your Python code, this will be done on the fly when you run the code. And comparing to ahead of time, which is for compiled language, for example, C or C++, where you first have to do the compilation and then run your code in a separate step. Numba works by compiling during running. So the basic good thing with Numba is that it plays well with all the scientific software stack that is used for Python, basically NumPy and SciPy. So as soon as you are using NumPy and SciPy, you're good to go. You can get the maximum performance. And as we will see while we go on, there is a way to make Numba work with all the Python syntaxes, but to make the best out of it, there are certain things that are not allowed, or basically there are certain things that are allowed, which will enable it to run in the best possible way. So as I said, Numba is compatible with NumPy arrays, which are the basis of scientific packages in Python. And one other important thing is that it allows you to parallelize your machine code so that all your CPU cores are used. So it's very easy to make a calculation parallelized to run on all your CPU cores. So make sure that you are running a proper kernel. Here I have Miniconda Python HPC, which I will be using. So this is to make sure that Numba is available as a package. And the first cell here, I make some imports that I am going to use while I go on. So the basic thing that is new here is that we import Numba. So most of the utilities that Numba provides are available when we import Numba. So let's start with a simple example. This is just a simple Python function that calculates, returns whether a given number is a prime. So if it's less than 0, it raises an arithmetic error. Then for 2 and 3, it returns true. And then if the number is even, it returns false, and then it uses a for loop to run and see whether your number is a prime. And as soon as it finds a number that it divides the number that you give it, it returns false. So basically what I do here is that I generate, let me run this. So I generate a random integer between 2 and 10 million, and I print whether it's prime. So it says to me that this number here that was random is not prime. Again, this is not prime. And is prime 1, it will raise the arithmetic error exception, as I told before. So how do we use, let me just run this. So how do we use Numba to do just-in-time compilation for this function? The only thing you have to do is to decorate this function with Numba JIT. So JIT stands for just-in-time, which means that it will do just-in-time compilation. So the first time this function, while we define this function now and I run this cell, the function is not compiled into native code yet. And I'm running this here. And this will run first the calculation for 10,000 numbers, which are random between 2 and 100,000. And it will return the numbers that are prime between these random numbers that we selected. And here I run the prime is prime jitted. Here you will see that it gives us some warnings. I will talk about it later, but basically we have here that the hold time was 508, while the hold time for the Python, the pure Python version, is 118. If I run again, we see that more or less now the warning went away, and we have more or less equal running times between the pure Python version and the Numba. So what's happening here? First of all, when I ran the second time, you didn't see the warning. And that's happening because the first time that is prime jitted is actually called, the compilation is being done on the fly by Numba. So that's why you don't see the warning the second time I run. And also you see that now the time is much slower than 500 that it was before. That's because in the first run that I did, the time included also the compilation time. So now the compilation is not done again. But we are talking here about performance, and basically what we get is just even worse time than the pure Python version. So what's happening? When I put Numba JIT here, Numba will try to compile the code that you see here, the function, but basically we'll use one of the two modes of Numba, which is the object mode, which is basically it will use Python objects when it does this calculation. But when we are talking about high performance, this is not what we want. So what I do here is I pass, you saw also this again yesterday, I pass the argument no Python equals true to the JIT decorator. and I try running. So now, again, you see that I defined the function, but this did not do the compilation. Only when I call the function, the compilation is going to be performed. So I run now, and now I get an error instead of a warning. And what it tells me is that it failed in no Python mode pipeline. So now that I told Numba that I don't want to run in Python mode again, it tells me that in no Python mode, it fails to compile. And it gives you exactly the reason. So Numba could not make a constant out of something that it decided should be a constant. And particularly with respect to strict interpolation, not supported. So you see here that some pure Python feature, like the string formatting here, it is not supported in no Python code. So I go here again in my code. I can go here and I can say number and remove the formatting. And now it's running fine. You see again here that the code is not executing very quickly, but that's because the first time it's called, it's doing also the compilation. So this timing is not correct. I will do now, and you will see the proper time. So pure Python is 12.8 millisecond, while with the no Python version of Numba, we are at 450 microseconds. So it's much faster than the Python version. And because what we want actually from Numba is high performance, we don't have to pass no Python every time. Instead, there is another decorator, the njit, which is equivalent to using Numba JIT with no Python equals to true. So this is what I will be using from now on when I want no Python mode. And I run here and I run again. So you see, I did this calculation 2 times. The first calculation included the compilation time, and the second one did not include. If I run the second time, since my function is already compiled, we get more or less the same time. So here we get the best performance. When you run outside of the notebook, you may want to compile once, but in the next run, you don't want to compile again your function. So there is this cas equals true argument that we can pass to the njit or the JIT decorator. Here I imported njit so that we don't have Numba and JIT all the time. I imported it by its name. So we use cas equals true, and again here we will not see a big difference because the cas is good for cases that you are running your Python script a lot of times outside of the notebook. So you see here the first time it compiled, and the second time wherever I run, it's more or less the same timing. So I have here something that I added the last days. I have the typical vector triad benchmark with Python versus NumPy versus Numba. Don't take the NumPy numbers that much into account because they depend a lot on the actual installation of NumPy that you have, whether it's compiled with MKL or it's compiled with OpenBLAS, etc. But I want to show you here how you can typically use directly NumPy arrays and compile your Numba function. So this is the vector triad, the pure Python mode. We range from J up to the number of, the J ranges from 0 up to the number of elements of the array. And here are 4 arrays basically. And each element of this array is equal to the element of B plus the element of C times the element of D. So this is the typical triad benchmark. This is the same in NumPy. So in NumPy, because we have vectorized code, we no longer have to pass indexes. While here, in order to get the best of performance, I don't use the NumPy vectorization directly, but I specify a for loop. And you see here that this is valid since Numba can work very well with NumPy arrays. So A shape 0 is fine for a NumPy array object. It can handle it. So here I initialize, I give some vector size and a number of iterations, and then I will execute the Python version, the NumPy version, and the Numba version, and we'll measure the megaflops that each of them achieves. So here, take into account that this is single threaded. If we go to a larger amount of elements, as I was testing yesterday, NumPy will start using all the cores, but for small sizes, it's using only one core. Here, specifically in the Numba version, I ran once, as I say at the comment, to avoid measuring the compilation overhead. And now I can run. So you see that a pure Python version achieves 3 megaflops of performance, which is quite slow. When we move to NumPy, it's 8 to 8. And for Numba, it's the best performance that you see here. It's close to 2000 megaflops. Numba has another thing that you can use in the ngit. There is an option that is called fast math, and this is going to take advantage of FMA. So it's not always faster, but if you're for some computation, you can take advantage of this fast math mode, and it will try to use FMA. So up to now, what we were doing with Numba is that we were defining a function like I did here. And as I said sometimes previously, when we call this function the first time, what Numba is actually going to do is it will check what are the type of the what is the type of the parameters that we are passing when we are calling the function. So here, for example, they are arrays of float 64, and it will compile a version of this function for this kind of arguments. If we call the function again with the same type of arguments, Numba will now have something in store for you. It will have something cast for you for this type of arguments, so it will not compile again. If though you call with a different type of arguments, so here if I call it with an NP int 32, for example, then since it will not have yet a version for this type of arguments available, it will have to recompile again. So the next time you call with an int argument, it will have the int version of the vector triad available, and it will use it. So you see that this is the essence of just-in-time compilation, that it also infers the types every time you call the function. But what we can do is actually tell Numba that we know the types that are going to be used, and we are going to we want it to compile to support only int32, for example, and int64 here. So ngit allows you to pass a list of function signatures that you want NumPy to Numba to support for this function. So here I pass two different versions. So this is called eager compilation by using the function signatures. So here I say that I want this function that will be compiled by Numba to support int64 and int32 numbers. Now I compile and I'm running, but you see here that it seems that there is no overhead. Let's go again. So what is happening here is that for the eager compilation, since we have provided the function signatures to Numba a priori, Numba knows at the time of the definition of the function that it needs to support these two different types of signatures. So the time that I execute the shell, the compilation is actually done at this stage. So it will compile two different versions, one for Boolean int64 and one for Boolean is the return type int32. So this is a C-like type of function signature. So if you are not familiar with C, just the return type and the arguments, the type of the arguments that the function accepts. And if it accepted second one, we could have, for example, float 64 or whatever. But I leave it as is for the moment. So I'm running and you see that there is no overhead. Let me do something here though. If I try to call, so A equals to so I create an int16 1, and if I see here, this is an int16. Now if I try to call the eager version of the compilation and I pass A, it tells me that this is wrong. I know only these function signatures, which were the ones that we passed during the eager compilation. So Numba is, when you pass it the function signatures for the eager compilation, these are the only function signatures that it's going to support. Since it does the compilation here, it no longer can do a just-in-time compilation for you when it meets another type of argument. So here it tells me that, well, I searched for an int16 version of your function, but we only support this kind of stuff. In this case, I could have done this. If I want to support int16, I would compile for int16, and then it compiles fine, but of course it gives me the error. Compile with 10, and now it's fine. So here I added another function signature, and now Numba compiled 3 different versions of my function. So each time I call this function, it will call the proper version of corresponding to the type that I pass it. So I would like to ask you if you have any questions up to now. Team, are there any Q&A?
So there's no questions in the Q&A. So once again, please feel free to ask a question just by unmuting your microphone and fire ahead.
Yes, is there something in the Q&A, or I can
There's
go?
nothing in the Q&A. No.
No.
Okay, continue.
Okay.
Oh, now there's something in the Q&A. Okay. So Marlon has asked, why do we say Boolean type in the signature?
So this is actually the return type of the function. So in our case, we need the whole signature because we are doing the year compilation. So we are saying that I'm passing inside the parentheses is what I'm going to give to pass to the function, and this is the return type of the function. So here I have the is prime function more or less, and it returns a Boolean. So it returns whether the number that I'm going to pass it is a prime or not. So one other thing also that I was planning to show later is that we have this function, and I can look at the signatures that it supports. So the signatures for it is only because the return argument is always the same type, Boolean, but what you are passing it is basically what your argument is going to be and where NumPy is going to differentiate. So you see here that it has 3 different signatures, one for int 64, one for int 32, and one for int 16. So is this clear?
Yep, it's absolutely clear.
Okay. Okay, so you have to pass it the whole signature so that Numba can do the compilation for you. So here is the return type, and inside the parentheses, you pass the types of the arguments. So if I had a second argument, I would use a comma to separate. So here again, I had this, but we showed it earlier, that now I use int 32, but I use float 64 here for NumPy to make sure that Python makes the conversion, and it will tell me again that, wait, you are passing me a float 64, but I don't have a function signature available for a float 64. So I only have these 3 versions that you passed me. If I didn't specify an eager compilation mode, then what Numba would do here is that the first time that it's called with a float 64, it would go and compile a version that would accept float 64. So within your compilation, you gain 2 things. First, you make sure that you don't have the overhead, and you compile all the versions of the functions at the time that you run this cell. So more or less at definition time, everything is compiled and not the time that is called. And also you make sure that you support only this kind of signatures. So if someone calls the function with a different signature that is not meant for this function, then this is an error instead of Numba trying to compile it, because when you define the function, it might have no meaning for float values, such as this case here, that there's no meaning testing a float number, whether it's prime or not. So I'll go now here to something more colorful. So is this clear by now? Yeah? I guess the raised hand is that it's clear. Otherwise, let me know. So now I'm going to demonstrate how we would run a more complicated kind of calculation, which is to calculate the Mandelbrot set and then use Numba to compile it, and also use the parallel mode of Numba that there was some questions yesterday, so we will see it in detail today. So what the Mandelbrot set is, basically is a region of the complex plane where by a certain recursive relation, the computation blows up, or you have that your points escape, and the computation works as follows. You divide your complex plane into a grid, and then for each complex number that corresponds to every grid point, you calculate whether this grid point escapes some radius that you give it. And to give it more color, how quickly you escape, into how many recursions you escape, gives it another color based on the iteration needed. So if you reach the maximum iteration that you allow, you assume that this point does not belong to the set, and you color it by the max iteration value. So don't take this too seriously by what this Mandelbrot set is, but what is important is that it's a calculation that has a double for loop, which is typical for scientific applications. You have two matrices, and for each element of each matrix, you do a double loop calculation. So I compile here a Python version of my code, and let's see how it looks like. So this is going to plot also the Mandelbrot set, and you see quickly that with Python it takes some time, and we are going to see how this is going to change when we go to Numba. So for pure Python, this calculation with a double for loop is an overkill, because for each I, it has to check what the type of it is and whether you have overflows and everything. So not overflows, whether you extend the bounds of the array and all of that. So you see here, this is the Mandelbrot set calculated by Python. It took 30.4 seconds. Now the same thing for Numba. So as we said yesterday, for parallelizing a loop, you, instead of using a bare range like the second loop here, you use a Numba p range. So let me disable it for now. I'll use a simple range, and I will pass the parallel equals true to the njit. So I use the njit here instead of using the JIT. If you were using the simple JIT, it would be JIT no Python equals true and parallel equals true. So it's the same as before. Now, since we are not passing a signature of the function, this is not compiled at this stage, but when we run function. We see here that the wall time is 293 milliseconds. Compare this to pure Python's 30.4 seconds. So this double for loop and the floating point calculations here and another loop here a while, pure Python is not very good at that. The thing to notice here is that Numba issues a warning for us. And it tells us that although we passed the parallel equals true, it could not specify by itself how to transform this code to a parallel one. So let me run again so that we don't include the compilation time. So 105 milliseconds. So here comes the thing that we were saying yesterday, that I changed this to a Numba p range. So basically this means that for each row of the matrices X and Y, this is going to run in parallel. So each thread, each core is going to take one single row of the array and work for it. So now I run, and I can run again. Now we don't see any warning for the parallel thing. And the whole time is now 11.2. So I will open just so that you can see. I open the machine resources here. Let me put it here. So here you should see the CPU. Let me run again. This was quite quick. I will run it for more iterations so that you can see that I will run for more iterations. Again, it's quite fast. So in this case, I will extend my domain here. Let me copy this and go here. So instead of dividing in 1,000 grid points, I will use 10,000 grid points in each dimension so that I can give it something to have to work on. So again, it's quite fast. We'll use more. So you see here that it reached 100%, and now it falls. So it took 10 seconds for it. The reason that you are not seeing a sustained 100% is that each Mandelbrot set point does not take the same amount of time to calculate, since other points escape more quickly than others, so they don't take the same time. So you see here now that this picture is actually much finer than this one because we have more points. I could give it even more points. Let's go to this and try to run. So now you see that I get 100% for more time, and it's fine. So there was a question yesterday, why don't we use p-range in both? And what would happen if I use p-range in both? Why not parallelize in both dimensions? So both for the rows and the columns. So I could use Numba p-range here. Let me use just this so that you will see what's happening. I do this here. Yeah, here it will take some time to plot because it's a large image. It's a fine image. So you see even finer now. So I am here. Let me close this. I'm here, and I have added a second p-range also for the J loop. I run, and now I try running. I run. This includes the compilation time, 42.8 milliseconds. Okay. Now let me remove the p-range. This includes the compilation time, 41.8 milliseconds. So what's happening here? I gave it a second Numba p-range, and I get more or less the same performance. So let's leave it here. Yes. You can unmute. Let me know.
Sorry, it was by accident.
So I'm again running this. I will see how we can check this, if it was by accident or not. So I have p-range in both dimensions, both for the rows and the columns. So the first time I had only for the rows. So each row would be taken by a single core, a single thread. And this time I split in both. So I have the Mandelbrot jitted. This is my function, Mandelbrot jitted. Now I have the p-range in both. And Numba gives you this functionality here that you can do Mandelbrot jitted dot parallel diagnostics to see what is actually parallelized and what is not. And I put level 3 here. And it tells me that the first for loop corresponds to 7 and the second one corresponds to 6. So it says to me here some information that attempting fusion of parallel loops, etc., and optimizing loop nests. And it tells me that 7 is a parallel loop, that 6 is rewritten as a serial loop. So parallel region 0, loop 7, had 0 loops fused, and 1 loop serialized as part of the larger parallel loop 7. So it realizes that extensive parallelization here is going to make the performance worse, and it doesn't do it. So even if I put the p-range for the inner loop, Numba knows that this probably is going to make things worse because each thread is going to collide with another and it will not have much work to do and it will introduce just overhead. So it tells you that since you already parallelized the outer loop, I will leave this one as serial. So let me write it as serial and let's see what it tells us now. Parallel diagnostics. And here you see that there was no problem. It just has a single parallel loop. So here you use the name of the function, parallel diagnostics, and you can control the level. This I have put 3, which is the top level, so that we see all this beautiful output here and know exactly what's happening. Any questions? Team, do we have anything in Q&A?
No, we've got nothing in the Q&A. I'll interrupt you if we have questions in the Q&A, no problem.
Okay. So I hope that this clears a little bit the confusion yesterday. So with Numba, first of all, by just putting parallel equals true is not enough. We have somehow to specify where we want the parallelization to take place. But also Numba is clever enough to prevent us from doing things that basically are going to harm performance in the end. So in our case, putting a Numba p-range here would not make our code faster. It will probably make our code slower because we already parallelized the outer loop. And so Numba knows that, and it gives us this information that we saw before, that it made the second loop a serial one. So let's go to something else now. We have here what NumPy calls a ufunc. So ufunc for NumPy is a function that we can call with an argument a single array, and this is going to execute this function to every element of the array. So if we wanted to calculate, for example, here the sum of sinuses of sines in two arrays. We could use the NP sine, which is a ufunc, an NP sine here. And basically what would NumPy would do, since this is a ufunc, is that it would take the whole array as it is, and it will calculate this function at the single element of the array. So you see here that we don't do a for loop or whatever. NumPy does this for us. And by doing this, it has a specialized version for sine, which is its version of NumPy sine, which is a ufunc, and it's vectorized to be as fast as possible. You saw before that if we try to do something like that in Python, the for loops incurred a very large performance bottleneck there. So NumPy allows you to create a ufunc on your own, and I have here created my sine, which basically, if I use two elements A and B, returns sine A and sine B. So by decorating my function with vectorize, NP vectorize, NumPy makes it a ufunc. So now I can use my sine as I would use its function. Oh, no, it's here. So I can, if I compile this, I can call my sine and array. It needs a second one, of course. Yeah. So now it does the calculation for us. So I can pass it arrays on the fly while without the vectorize here. Tells me that only size 1 arrays can be converted to scalars. So by using NP vectorize, we have a version of our ufunc that we have created that did not exist in the standard NumPy library, and we can use it with arrays. But there is a problem with that. The problem is that the functions that the ufuncs that NumPy already provides are compiled and they run completely vectorized. While here, since NumPy cannot compile like Numba does on the fly, this is just a wrapper so that NumPy will create, more or less, will do a for loop for us. And basically, this is just pure Python, just being able to accept Python arrays. So you will see that the performance is quite bad. Numba, on the other hand, allows us to use Numba vectorize, and since it can compile on the fly, we can create compiled versions of these ufuncs. So let me delete this for the moment. Notice that when we use Numba vectorize, we'll have to pass the signatures as we did in the eager compilation, but this time they're not optional. You have to pass them, what you are going to support. So in this case, I could pass the strings, but I just use the other convention here. I imported the types from Numba, and I use it like that without strings. So basically, I tell Numba that I want to create a ufunc which supports 2 float64 arrays and 2 int64 arrays. I compile. This is, since we are passing also the signature, which is not optional for Numba vectorize, this compilation is done right here. So I will move from here, and I create 2 arrays of 9 million random integers, and I run. Let's see the timings. So For NumPy, this was 480 milliseconds. For Python, it was 3 seconds. And for Numba, it's close to the NumPy performance. Again, let me run. More or less on par with the NumPy performance. You see here that although I did use the NP vectorized, which is the second one here, it is just a nice way to not having to run the for loop myself. So it cannot compile on the fly, but it just wraps the for loops for us. While here, I compile on machine code directly. Any question?
Yeah, there's a question. So I think this refers to the previous example. It's from Francesco. So he would like to know if there's information like this for SIMD, something like parallel diagnostic, but showing if there are any obstacles to loop vectorization, for example.
Okay, so I will show this in the end. Let me finish with this, and I will show
Okay.
you what kind of information the function can give you.
There's one more question then from Camila.
Yeah.
Why are number functionalities? Why aren't number functionalities embedded by default for every Python function if it makes code potentially faster?
Why not? Can you say it again? Can you repeat?
Yeah, I've put it into the Slack channel at the bottom.
Check. Yeah, so this is not happening because, as we saw, Numba works for a subset of Python and a subset of NumPy. So you cannot put Numba everywhere like you could have it standard inside your library. So this it would not be able to compile everything, since it makes the code compilation. It's not able to infer and create machine code for every Python code out of there. So it's only meant to be used for this kind of calculations, scientific codes, etc., where you have this for loop type of needs. So it will not be able to do that. So let me finish onto that. Here we have Numba vectorize, and we have a way to tell it to parallelize it also. So in our case, it's not parallel equals true, it's target equals parallel. There are other targets as well, like CUDA, that you can make it vectorize things to be used on the GPU. I use parallel here, which is the parallelized version of the CPU. So let me run. So this time, we went from more or less this hold time here to this hold time here. So it's 5-6 times faster. So we need to go to larger array sizes to have the proper speed up, but even with that size, we already have a 6 speed up. The important thing here is that just by telling it that I want you to target a parallel machine and parallelize the code, it just parallelized it for us, just by using the target equals parallel here. And now to close, we saw before that we were using the isPrime function, but actually since we can use the Numba vectorize, we can pass it a whole array of int64s, and it will return more or less an array of whether each of these numbers is a prime or not. So I use the isPrime v here name, And now I create an array of random integer of size 100,000, and I check whether and which of them are primes. Now I do the same here, is prime VP, but now my target is parallel, and we will see. Oh, I didn't compile here. So I time here. You see, it's more than 10 times faster here by just adding the target equals parallel. And now I can print the largest primes that it found from 1 to 10 millions. I create here an array from 1 to 10 millions, and I want to find the 10 largest primes here. So I do it parallelized, and here are my numbers, just by using the Numba vectorize here. In this case, I told it that it accepts both Boolean int64 and int32, and it returns a Boolean. So any questions? No questions? Please make a question if you have now. Team, they don't have any question? Team?
No.
No question. So I think that it was up to 10, and we should make a break, right?
Yes, we'll have a 15 minutes break.
Okay, so let me know, first of all, because I have more things to say for Numba, if you would allow me to steal some 15 to 20 minutes from Cython, if you like this Numba thing, raise a hand so that I can show you some more things. Okay.
Yep, looks like it's quite popular.
Okay. Okay, so I want to show you some more functionality, and also this thing that we have missed to show you how you can see more of what code is generated by Numba, and some other applications of a Numba stencil, and then we can proceed with Cython. So, okay.
But we'll keep the break now as scheduled, and then we'll continue after at 10:15, correct?
Yeah.
Yeah, okay.
So I'm making the host now, and you're host now, right?
Yes.
Okay. I'm disconnecting and reconnecting. Kim, can you make me host? Okay. I guess you can see me now. So I guess we can start. So is everybody back? Please raise your hand. Good. Okay. Okay, so let me go a little bit here. We had a parallel diagnostics thing, and I have this function here. This will answer the question of how you can go into more detail and see what Numba is actually doing under the hood. So this is actually an object, Mandelbrot cheated. The function is CPU dispatcher object of Numba. So it has some properties. It has signature. So here you can see more or less this is a list of signatures that Numba has compiled based on what it has found out when it did the compilation on the fly. So basically, it just tells us that it receives two 2D arrays, as you see here, and one float 64 and one int 64, which were what we passed the first time that we called it. So X and Y were 2D arrays. 4 was a float 64 and 100 was an integer. What you see here is an interpretation of arrays by Numba. So it says that they are float 64 arrays, they are 2D, and the C here is that these arrays are expected to follow the C convention, which is row major. There is a way to make it work with Fortran-based arrays, which are column major. I can go into more detail if you want, but you can also look at Numba's reference manual for this. So what we can do by this, we can get the first signature, which is this here. Also, this Mandelbrot JITed gives us a number of functions. I started with the I here, and it has some inspect versions of this. So I can inspect LLVM. Let's ask what is here. So it says, get the LLVM intermediate representation generated by compilation. And also it's waiting for us to pass it a signature. So as we saw before, we can have many different signatures that depending on how we have called our Numba function. So here I'm going to pass it signatures, the first signature, which for our case is the only one. Let me also put print so that we have a nice printing. So again, I'm calling the inspect LLVM version of this Mandelbrot JITed, and I pass it the first signature of the function. So here it's going to tell me and show me what was the intermediate representation, the LLVM intermediate representation that it created. So you see here that there are a lot of stuff going on. A slightly shorter thing is if instead of inspecting the LLVM, I inspect ASM. So this is going to show me the assembly language that it has created. And from here, it is easy to see actually if you need whether it has created SIMD based, if it has used SIMD instructions and so on and so forth. In general, it is SIMD aware, so it's going to use the SIMD instructions. We can see the same when I go to the vectorize function is prime VP, or to our vector triad thing. So let's see for the vector triad. Let me find it. There's a lot of stuff here. So this is in general when you want to go and see what it has done and what it has produced, and whether the code is has the optimizations that you want. So let me go to the triad. So the vector triad here, we have the vector triad Numba. I will put again expect ASM and signatures, the first one. So you see why I put print in the first place, because otherwise it does not print nicely. So again here, if you look into it, there are actually SIMD instructions that it has generated. So we are taking full advantage of our machine. Any questions up to now? Or can I move to the stencil?
Looks like you can move. Oh, wait. Yes. Yeah. Yes, you can move.
Hmm?
Yeah, feel free to go ahead.
Okay. So now we go to something a little bit more interesting if you are into, in general, partial differential equations. So I'm closing this here. And let's go to the Numba stencil. So stencils are typical computational kernels in scientific computing, especially finite difference methods for solving PDEs. Numba offers a stencil function decorator, which allows you to define stencils, and we will see how. And it's very nice because you don't have to write the loops yourself, and also you don't have to handle the boundary conditions, it handles automatically. So just to make sure that we are using the correct kernel. So just a little bit of math. This is the 1D heat equation. So what you do with finite differences, more or less, is that you split your domain into a grid, and then you substitute the differentials here with finite differences. So here we have one 1D domain where we split into many elements. We have the grid points, and in each grid point, the temperature UI, we will use the neighboring elements to calculate the partial derivative here. So instead of having a differential equation, we go to a difference equation here. So with n plus 1 here and n, I have the time. So by starting from time 0, we can proceed into calculating the temperature in later time steps. And here is the typical stencil. So more or less, we have the stencil that we substitute the second differential here, the second partial derivative here with a difference. So we have -2 times the central point, and we add also the neighboring points. And this happens for each of the points of the 1D domain. So typically what you would do for this is to go and write a loop for all these points by hand. And you would say that for each of these points, this holds, and you would solve this equation here. And basically you arrive at a point where each temperature at time n+1, let me make it bigger here, at n+1 is the previous temperature of this point and some previous temperatures of the previous point. So this is true because I used an explicit finite difference scheme here, which does not, which means that the temperature at a different time step is completely defined by the temperatures of the neighboring points at the previous time step. So it's pretty easy to calculate the temperature at the next time step. So we have the 3-point stencil. Here I do some necessary initializations. I don't want to go into more detail, but more or less it's just to define a domain and define some parameters for my temperature, for the heat equation and for the initial temperature. So we have here our I didn't run this. Yeah, make sure that you run this first and this. And then I go here and I define my stencil. So I just have to write, as I said before, what is the more or less the relation that the stencil defines. So here we saw that our stencil is UI, which in our case, I will say that it's my 0 point. And we have UI0 plus F plus UI times UI plus 1 minus 2 UI plus UI minus 1. So this means that if UI is U0, then we need also the neighboring point temperatures. So I just write the stencil like this here. His x0 is my temperature at this point. X1 is the point on the right. X minus 1 is the point at the left. So that's it. That's my stencil. And I give the Numba stencil this, and Numba will recognize and will create a stencil function for me, will handle the boundary conditions without me having to do anything. So I run this, and now I define the function simulation, which just does the calculation of the temperature by proceeding through the time steps. So I just call the central difference stencil, which I have defined here, with X and F. And every time I have the X updated. So I have my simulation thing here, and I will plot the final temperature distribution as well as the initial. So in the initial temperature distribution was this one, and at time 100, we see that the temperature has spread to the neighboring elements. So I didn't have to go and write a for loop for all the grid points of the stencil. I just defined what's the relation of the that is specified by my stencil. So I could have used here x1, for example, and here x2 and x0 here, but just to be clear, I used that as 0, the point that I'm interested in, a general point, and its relation with the neighboring points here. Any questions? I will go to the 2D after that to show you that this is true also for 2D grids and 2D stencils. Okay, I guess I can proceed. So again, these are here some parameters. You can look at it into more detail and ask me on the Q&A today if you need something. But I want to proceed to show you also the 2D because we have a lot of things to say in Cython as well. So for 2D, we now have, again, the coefficient A, and now we have two partial derivatives, which are for axis X and axis Y. And now, instead of just having, we replace here the second partial derivatives. Oh, sorry. Okay, so I replace here the two partial derivatives with differences. And now let's take a point at the 2D rectangular grid. We have Ly and Lx and Ly are the domain sizes on the x-axis and on the y-axis, and a general point Uij. The temperature at point ij is Uij. And here now we have a 5-point stencil grid, 5-point stencil, because our neighbors lie also on the x as well as the y-axis. So now our Uij will have to take into account the Ui minus 1 on our left, Ui plus 1 on our right, Uij plus 1, which is on top of our element of interest, of our point of interest, and Uij minus 1, which is at the bottom of it. So if you have a general point here, you see that I have to take point here, the point here, and point here. So more or less, this is the relationship for the finite difference. You see here that I have Fy, which is now a parameter that depends also on delta x, and I have Fy, which is depends on delta y, as I write here, and they depend also on the coefficient of the differential equation, as well as the time step. And now the grid, we have the 2D case, and now the stencil looks like that. So you see that for a point x that is our point of interest, and I define x0, 0, I have a dependence on x minus 1, 0, which is the point on the left. The same point, of course, is taken into account, the point of interest. The point on the right, which is this, and then I have the point on below and the point on top. So I run here. Now my simulation 2D is again the same. I just proceed over time, and now I will plot how it is. So this is my initial temperature. It's just, you see here, it's like it was in the 1D case, but projected in the 2D now. And this is my final temperature. You see that the temperature distribution has spread, and we have also lower temperatures. You see the top here is 0.32, while here it is close to 0.95, the top temperature. So here my temperature is 0, which is the initial conditions, and my final temperature is this. Note that you can specify also different boundary conditions. There are ways to specify your boundary conditions in the stencil function. I don't want to go into more detail, but I wanted to show you how you could, if you're interested in finite difference methods or other grid-based methods which use stencils, you can take advantage of the functionality of Numba without having to write the for loops by yourself. Any question? Tim, is there any Q&A?
Hello. So one question has just come. So Louise is asking, is it possible to parallelize the step of simulation? Simulation steps.
We cannot parallelize it because we have to move a time step at a time. So each time step depends on the previous one. So it doesn't make sense. You cannot parallelize this.
Okay, and then there's a question from Hari. Is it possible to specify a derivative boundary condition instead of values?
So I think there is a way to do that. You have to look into the stencil function, the stencil decorator or function of Numba. We can look at it here. Yeah, it doesn't give me. It has some options and func or mode that it says here that lets you specify various things. Maybe you can do it by using a certain function, but here I didn't use this because I just wanted to show you how you can define your stencil just simply like that by just using the relation here.
Okay, thanks, Theo.
Okay, so I guess that we can now move to Cython. And let me just close this. Again, if you have any questions, after you see a little bit in more detail the notebooks, you can ask me at the Q&A session. So I will be glad to answer whatever you might didn't understand correctly, or something else that you might be interested in regarding Numba. So this is not the end of Numba in our course, because tomorrow you will look into how you can use Numba now to accelerate your code by targeting the NVIDIA GPUs. Since we have NVIDIA GPUs, we will show only the CUDA functionality, but there is also functionality for AMD GPUs by using ROC. But this CPU functionality works regardless of Intel or AMD CPU, so covers both cases. So now I will go into the Cython part. You see here Python HPC. I go to Cython, notebooks, and I will start with Cython 1. So the things that I'm going to say, if we have time, I will show you also Cython outside of the notebook. But I think that it's starting with Cython, it's very nice to see using the Cython magic that the Jupyter Notebook has, which allows you to compile C directly from the notebook without having to first compile by going outside and then running. So I will start as this notebook shows. So optimizing Python code with Cython. So Cython is basically a compiler for Cython code, for Python code, and it allows you to compile your code directly to C. And this has two advantages. One is that you can, like we saw with Numba, you can go and compile certain functions that are very computationally intensive, and so gain native speeds for these functions like Python, like Numba did. It's not just in time, so we will see just in time, so we will see the differences with Numba. And the second advantage is that using Cython, you can basically wrap libraries that you already might have or somebody else might have written in C and call them like there were Python functions, but in the same time using the native C speed. So these are the typical imports like we did before. I will change now to the Miniconda Python HPC kernel. Come on. Let me open it again because okay. So it's not letting me. It seems there is a problem with my notebook. Let me stop and
Yeah, it looks like there's some kind of issue with the network at the moment. My notebook's also stopped working, and so has at least one of the participants.
okay.
Could be that there's a file system issue.
Let's see. So is everybody else connected, or I'm the only one that's having issues?
No, no, I think all of us are having issues at the moment.
Okay. So
hopefully it's just a temporary network issue. Let's just give it a couple of minutes and I'll check with the file systems guys.
okay. So in the meantime, I can show you in my local machine. Oh, I don't want that. Okay, so I can show you in my local machine how it looks like. So notebooks, one, start, waiting to connect. Okay, so just so that we don't fall behind, as I said before, we have to do this. Okay, we are in. No. No. So as I said before, this is going to do some necessary initializations here, and I import Cython so that I do this thing here, which will load the Jupyter Notebook Cython magic for me. So now I'm running locally. Bear with me so that until the Jupyter notebooks come back. Let me see. there is something. Oh, waiting to connect. So can you see my notebook?
Yep, we can see the notebook.
So optimizing code with Cython. Again, I do the necessary imports here. So yeah, I run second time. So it tells me that it's already loaded. So let me introduce you to what I'm going to do now. I have a pure Python version of the Monte Carlo simulation method of calculating pi. So basically what I'm doing here is that for a number of times that is specified as 1000, the default number here, I throw pebbles on, I throw points inside the circle, inside the square, and then I check the number of, in the end, the number of the points, whether they lie inside the circle, a circle of radius 1 or no. And by dividing how many of these random points have been thrown inside the circle, I can calculate more or less pi by dividing by the number of total points. So here you see a 4 here because I just use only the first quadrant of the square, and I can calculate pi like that. Let me calculate using pure Python, and it took me 2 seconds. Let me see. No. Okay, so it took me 2 seconds with pure Python. Now, in order to use Cython, so to calculate the same thing, but now compiling into C, we have to use this decorator, this magic thing on the notebook cell. So we have %% Cython, and it's basically the same signature here, the same function definition. What I want to say now is that nearly all Python code is, let me see, okay, we are in. All Python code, 99% of the time is also valid Cython code. So if I run this is compiled with Cython now, and I run, and I went from 2 seconds to 1.25. And again, you see that I have more or less the value of pi here, depending on how many times you run the experiment, the Monte Carlo experiment. You might have a better, you might have a better calculation of pi. Okay, so we are in.
So maybe we can just have a quick show of hands to check if other people have got their notebooks back. My one is working now. Yeah, 3 or 4 people. If it's still not working, maybe just try refreshing browser first of all, and then otherwise try to launch another notebook when you get a chance. Hopefully everything should be back to normal. Thanks, guys.
So we're just here, like I said, changing this by adding just Cython tells the Python notebook, the Jupyter notebook, that this is going to be compiled with Cython. I compiled, and I went from 2.95 seconds to 1.53. So I already have a speed up by changing nothing. So are we doing this just for a 2 times speed up? The answer is no. Here you see that we have the Cython notebook magic. But actually, we haven't given any more information on Cython, on what to do with and what our types are, etc., etc. So it cannot infer these things for us, like Numba did, and compile in the best possible way. So to make sure that it is compatible 100% with Python, it doesn't introduce many optimizations here. It compiles into C, but it uses Python objects instead of using integers or what other types we have, which are the primitive types that C has and are the fast ones. So we have a lot of overhead since we want to make sure that this is compatible 100% with Python. And you see that we only had a two times speed up. So Cython, the more information you give it about the types that are being used inside the function, the more it can do for you to optimize your code by compiling using the corresponding C types. Here comes the keyword cdef that Cython uses. You use this keyword to step out of the dynamic nature of Python code and produce efficient C code. So instead of just having int circle equals 0 here, I have cdef int in circle equals 0. So I tell Cython that int circle is an integer. I also tell it that I, which is the index of the loop, is also an integer. And I tell it also that x and y that are my temporary random variables, basically the coordinates of the pebbles that I'm going to throw inside the square, are doubles. So now I have defined types, I have declared the types for my variables inside the function, and I run again. Now let me run this benchmark run again with the same number of points. Remember here, without using any types, it was 1.53. Now, by using types, I fall to 357 milliseconds. So you see that the more information I give to Cython, the more information it has to use the proper C types and make my function faster. So here I went to 0.3 seconds more or less instead of the 1.53, which is quite a speed up for just having to introduce these types here. So in the first case, the int circle, as I said, since it didn't have a type, it was a Python object. Although it was compiled in C, it was still a Python object. But here it's a C integer. So for those of you who are familiar with C, you see that like C, I have to declare what types my variables are here. Instead of using the cdef word all the time, you can use another version of it. So you have cdef, and you tell it that cdef and colon here, these are all cdefs. So instead of using cdef all the time, I just use it once, and inside this block, I do all the type declarations that I need for my functions. Also here, you see that I did it for my argument as well. So I know that n is an integer that is going to be passed, and I pass it also here. I give more information. Here, I use the Cython magic of the cell again, but now I pass the option annotate. So what this is going to show me is, like we had with Numba before, it will show me more information about what code Cython generates. So by running, it says generated by Cython 0.2913, so we are fine. And here you see that it says that yellow lines hint a Python interaction. So these are the points that actually are the interfaces with Python. And whenever you see this yellow, and depending on how deep this yellow is, it means more interaction with Python. So here, if I click, you will see a lot of C code that is generated. Let me click on it. You see here in the C defs, I have no Python interaction. Here I have Python interaction because random is a Python function, but it's again defined at the C level, so it's fine. And since I return a 4 times in circle over n here, and this does not have a type, it again has a Python interaction. We will see how we can reduce that to optimize more. So if I do the same thing here, with the initial one, you will see that I have a lot more Python interaction, because now all of these are Python objects. So in circle is a Python object, and XY are Python objects. Here we do the calculations using Python object. Here again, it's a Python object. It's instead of an integer, and so on and so forth. So with the annotation, you can see how much interaction you have with Python, and in terms of performance, this is bad when you interact with Python. So is it okay up to now? Any questions?
Yep, there's a question. So Camila asks, is the code faster with CDEF because it can use more efficient memory allocations for the data types?
Okay, so of course it uses less memory and better memory allocation, because instead of having a whole Python object and whatever information a Python object needs, the integer is better, because this is a C integer, which is 4 bytes in this machine, but also because all the calculations, all the computations are done using C integers now, and not using Python objects. So instead of doing just a simple addition, it would need to see what the addition means for that particular Python object. So it takes much, even if we had, it's not only the memory footprint and the memory allocation, it's also that it has the information of the types to make now the computations in C level, but without using Python objects. So this is just the X times X calculation, and it doesn't pass through the Python object creation or whatever. Other questions?
No, that's all good. You can continue.
Okay, so as I said before, I have heard also in various Cython talks to talk about gradual typing. So Cython gives you this so-called gradual typing, so you can start introducing type declarations in some of your variables, and start migrating more and more from 100% Python code to 100% C code, and have the interaction with Python only at the calling level. So the more info that you give in the site, in what you want to compile with Cython, the more it can take advantage of the native C code and do the calculations in a better way for you. Now, you saw here that I was using def, even though this is a function that is going to be used, it's going to be compiled with Cython. So Cython has three types of functions. Function declared with def, as we saw before, can be called from Python and also from Cython code. So we can have various Cython functions. The functions defined with def can be called both from Python and also from Cython code. Then we have the cdef functions, like the one that I will show you here. So cdef functions are not visible from Python and cannot be called from Python. They can only be called from other Cython code. And then we have the cpdef, which basically is a fusion of the cdef and def. The difference now is that Cython, when we are using cpdef, Cython will generate two function versions for us. And when we are calling the function from another Cython function, Cython is going to use the cdef version of that function. When we are calling this function from Python, then the def function version is going to be used. So basically, it's like defining both def and cdef for this function. And Cython decides for us which should be the appropriate one to use. So I define here a function cdef, which is double. With cdef, you pass also the return type of the function. Cdef double cube, which is basically just a function that will calculate the x, the third in power of 3. And here I have a cpdef. Since this is a Cython, a cpdef function, inside the function I can call a pure cdef function, while this cube function will not be directly visible for me from Python code. So if I compile this, I can use also the annotate to show you. You see here that in cdef double cube, this is a cdef function, and I have everything defined here, both the return type and also what the parameter type is. There is no Python interaction here because this is compiled in pure C. And also you see here that I have this interaction in the calling of cube sum. So it's just the sum of the cube of two numbers, the cubes of two numbers. But here I don't have any interaction with Python because I call the C compiled function here. So just to show you, make this mistake all the time. So just to show you what this means, I can call cube with one. What do you think? Will I be able to call cube directly? No, name cube is not defined. In this case, I cannot call it, since this is only visible from another Cython function, while cube sum I can call.
Theo, we have a question from Giordano.
Yes.
Is it possible to template functions, i.e. make it work with more types?
Yes, there is a way, and I will show later if we have time on how you can use templates also. And this is also this also means that you can wrap C++ codes that has templates. So you can wrap functions like that from C++. For the moment, I'm showing pure C and not C++ things. So you see here that CubeSum I can call, and cube is not visible. If I do cpdef here you see that now I have an interaction. But here, while calling cube from another Cython function, I don't have interaction with Python. This is because, as I said before, from inside the Cython function, Cython will call the cdef version of the cube, while the def version will be called only when we call cube from outside. So I can call cube now here, but with the cpdef, I have two different versions of cube compiled. One, which will be used whenever there is interaction between Cython, 100% Cython, and the other one, which will be used when I call this cube from Python code. So is this difference clear? So on the one hand, you have cdef, which can be called only from other Cython code. Second, you have the typical def that can be called both from Cython and Python code. And then you have cpdef, whereas when you use it from, it does a compilation of two different types of function. One that is completely in C, which you can call only from Cython, and one that you can interact also from Python. Any questions?
No, it looks like it's clear.
Okay, so now we can proceed, and I can show you also this cdef inline for functions. So for those of you who are familiar with function inlining in native C, there is also the cdef inline. Of course, it's not applicable for functions that are called from Python, but for C-only functions with cdef, I can inline the function. So actually, this gives a hint to the Cython compiler to, whenever it sees cube here, it will replace it with the body of the function, so that it does not have to do the to incur the function call overhead here. So I can compile like that, and this will make sure that Cython takes this into account. And we can, for small functions, this is really a good optimization option to avoid having to pay the function call overhead. So if you have to call a small function many times, then you can you don't have to pay this function call cost by using the cdef inline. Cython will take this into account and will replace the function call here with the function body. So it would go and use the x times x times x here and y times y times y here. Okay. Okay, so I can proceed now with something that is quite nice with Cython. So Cython is compatible with NumPy, which again we saw that is the typical backbone of scientific computation in Python. So you can have like that here. Here I introduced a double array, which from the Cython point of view, type NumPy arrays are handled as memory views. So basically, I tell Cython that this mySum function accepts a typed memory view, and you see here how the syntax is. So I say here that this is a double typed memory view with a single axis. So it's 1D. Here again, I have the typical CDEF int y and y, and ny is equal to the first dimension, the first extent of the memory view that I pass. So now I can do the for I in range nx and sum my array. So I do it here, and see here that there is a slight interaction with Cython, with Python, and we will see how we can reduce this interaction also. So again, this is the way to tell Cython that more or less this is compatible with a NumPy array. So I can pass now a NumPy array, and this function can work with it. And we can see it here. I passed an array of ones of float 64, and now I use the mySum and the NumPy sum here, which is the method of x. Here I use my Cython version. Of course, it's the same. Now I can do the same thing, but for 2D typed memory views. So as I said earlier, this is the syntax for memory views. So now, because we have a 2D memory view, a 2D NumPy array can be passed to it. And here is the syntax. You have colon, comma, colon inside square brackets. So now I can take both the extents of the array. So this is the shape, the 0 shape is nx, the 1 shape, which is the number of columns is ny, and def again, and now we have a double for loop. I can do that. Again, we see there's an interaction, a slight interaction with Python here, but now I can do the summation and everything is fine. So this function accepts 2D arrays, 2D NumPy arrays as well. So we see here how we can make Cython work with 2D NumPy arrays as well. Now, you saw here that there was an interaction with Python. And what is actually happening here is that we are passing typed memory views, but again, Cython has to make the check that we are not out of bounds of this array, so that we don't use an I that goes more than the shape 0 and a J that goes beyond the number of columns of X. But since we are already using nx and ny, which are the shapes of the array, we are pretty sure that there's no problem, and we don't have to do an additional check every time for I and j to make sure that we are out of bounds of the array. So we can use this here. When we import things from Cython to be used in a Cython code, a Cython function, we use cimport instead of import. So from Cython, cimport wraparound, I will tell you what this is, and bounce check. So the bounce check we decorate the function with bounds check false. So now we don't have to do the checking for all the indexes of the loops here that we are out of bounds. And wraparound means that since we are dealing only with positive array indexes, we don't want to make an extra overhead. We don't want to pay an extra overhead for negative indexes that NumPy allows and do the wraparound for this negative index. So negative index would mean that -1, for example, is one index, one element left from the end of the array, while we don't want to pay this overhead. So we can compile like that. And now you see that we no longer have to pay the price of interaction with Python here, which was the case. Notice here that this is not a very serious interaction. You see here that yellow is not as deep as this one here, which is true Python interaction. It is here it's more pale. While here, by not doing the bounds checking, we don't have to pay this price at all. Any questions up to now?
Okay, so there was just a question about using pointers with Cython, whether it's possible.
It is possible, yes. Yes, yeah. It is possible. I think that we will see it after, but if not, I can answer to it at the Q&A, or if we have time for it. So yes, whatever you can, basically, since you can wrap whatever function you might have in C, you can declare pointers in Cython as well. And again, you use this notation with a star sign. But this is something more advanced. And also, when you use pointers, you lose this type safety that you might have, since with pointers you can do some other stuff as well. So in general, when you are passing NumPy arrays and you want to be compatible with NumPy arrays, you use this thing here, the typed memory views.
Thanks, Theo.
Okay. So now let's go into something more interesting, releasing the GIL and parallelizing loops. So like we had with Numba, we again have a p-range function here, which is the equivalent of range but parallelized, that we can use also with Cython. So here I compute something that is quite close to the Mandelbrot set, which is called the Julia set. So in this case, we have to pass also, except of the X and Y and the maximum number of iterations and the radius that we have to check whether our points blow off and explode and go out of the set and are into the set, I mean. We have to pass also more or less the complex, the real part and the imaginary part of a complex number. So this number will make us, will differentiate the Julia set that is going to be calculated. So again, here we have the calculation like we had in the Mandelbrot set. The recursion is a little bit different, but basically, again, for each point of a 2D grid, we do some computations. So here I used all the typing that I can use. I used the CDEF with the syntax that I don't have to write cdef a lot of times. I declare all my variables, all my parameters here. Note that you can use also const, which means that this the values of x and y here are not changed within the functions. So it's, for those of you who are familiar with C, it's exactly the same thing. I mean that I don't change the values of x or double the value of cy and cx here, and the number of iterations and the radius is constant. And the only thing here is that I have to allocate a Julia array, integer array beforehand, and I will pass to the function, and this is going to contain the values of the Julia set that I want. So I don't return the Julia set, I pass it to the function. So let me compile this. And now I will create a grid of points, x and y, and I will time how much time the Julia set takes. This is again the C, and I can take the real and imaginary part of C to use for CY and CX and CY here, and I run my Julia set calculation, and you see this. I can change the picture if I change the value of, oh, sorry, changing the value of the complex number here will change the Julia set produced. So you see, you can play with some values here and have different interpretations of the Julia set. There are different Julia sets. So basically, this C is used in the recursion here, where you calculate how much you have gone away from the radius, the absolute value of the norm of the imaginary number has exceeded the radius and whether or not. So by using this, so just to have the same measurements, if you try to do this computation in pure Python, it will take ages because of the double for loops and the while loop. As we saw for the Mandelbrot set, when we used the pure Python, it did about 30 seconds. So here I do time it to run a lot of time also, a lot of times to make sure, and it takes 746 milliseconds to calculate the Julia set. Any questions? I guess it's fine then.
Yep, continue.
Yeah. So now we arrive at the p-range thing. From Cython C import, bounce, check, wrap around again. And now to use p-range like we did from Numba import p-range, here we have to import it from Cython.parallel p-range. So I go and replace the range loop here, the first loop, with a p-range loop here. I'm running. So we were in 700 milliseconds, more or less. And I will run the calculation again here. But what's happening? I use the p-range. And I have again the same type, although I use the p-range. So what is actually happening, I have deliberately made a copy of the function here so that you don't directly see the answer, is that as with Numba, if we don't use the parallel equals true, Cython has something equivalent. You have to specify the compilation linking options so that it knows and compiles with the correct flags so that it can take advantage of OpenMP, which is uses for p-range here. So in our case, for the Cython magic, this is the syntax. So you have to pass what you would pass to enable OpenMP in your C code. So extra compile flags, compile args are F OpenMP. I passed also mark native. You can pass other options as well for compilations, for the compilation with C. And extra link args, this is to link with OpenMP. Again, the same thing with p-range here. I compile, and let's run now. Before it was 746. Let's see how fast it is now. (164). So it's about 5 times faster. And here it may seem slower, but it did more calculations since the function itself takes less time. So by doing this, I tell it to run 1 iteration and time it. 166. So I can go to even larger domains. This will take more time to plot actually. The computation has been made and it takes advantage of all our cores. So let's use this machine resources thing to make sure. So you see that it went quite high. I will put more iteration here so that it has more things to calculate. And I press, and you see the resources, it reaches 100%. And as I said, the load is not equal because some points escape very quickly and belong to the Julia set. So you see here that as time passes, it uses less and less CPU time. So using p-range, you have to remember that it's not enough. You have to pass also the compilation flags here. And since Cython uses OpenMP to parallelize things, you have to pass the proper compiler arguments for the compiler. In this case, it's the compiler is GCC, and I can do this here. So yeah, now it takes a lot of time because I put a lot of iterations. We'll stop it. And do we have any questions? Also, one thing that I didn't say, and it's crucial, is that in p-range, I pass this argument, the no_GIL equals true. So because we are in C code, there's no reason to have the GIL enabled anymore, so we can release it to use multi-threaded code.
Theo, we have a question.
Yeah.
So you mentioned that the compiler is GCC. How do we know which compiler it's using under the hood?
I think with annotate, it says it. Let me see. Let me stop the kernel. Attach a new one. So let's go to this. No, it doesn't say here, but you can see from the Cython. Let me see. Cython dot. There is a way to see it, but I don't remember exactly. If you see it from here, or there is an info thing. Yeah, there is a way to see it, but I will. If we go outside of the notebook, for sure we can see it. Like if I go here. Yeah, there is a way to see it, at least when you compile, that you know which compiler it uses, and also you can define which compiler it sees more or less and uses. Let me see. Yeah. Yeah, so I don't remember the exact option, but you definitely can see it, and also change the compiler that it uses by default. So any other question, or I can go on?
You can go on.
Okay. Let's select our kernel. Again, here. So what I told you about Python inferring the types, well, this was not exactly true. You can make it infer the types for you. It's always better to specify directly the types, but you can make it infer the types. Or from Cython import infer types. So here you see that it has inferred this because there's no interaction with Python. And if you go into more info, you see that it gave this value, this, and there's a lot of code here. But if we actually go to where the function is, you will see that this is an actual C integer, because it inferred the types for you. So by decorating the function with infer types true, you don't have to specify the CDEF for the types that it can infer. Here you see that it was able to infer it. If I don't initialize and use it after, it won't be able to infer it. So it's always better to use CDEF when you know the types that we are going to use to make the best of the compiler. So again here, it's faster. Okay. Now, like we have Python functions, we can have Cython functions. Here, you see that I have defined a class PyRectangle. It's nothing, it's very trivial. It's just a class that has two fields, an X and Y, and it's basically a rectangle class, which with the lengths of the two sides, X and Y, and it can return the area and the perimeter here. It's very simple. And I could have P equals PyRectangle 1.2, and I could use perimeter 6 and the area at the same time. How do we do with this with Cython? Notice the differences here. Instead of class, I now have CDef class. I name it PyRectangle here. And instead of having the fields directly inside the init, I have to declare them here. So I have two fields, double X and Y. And instead of the init, I have CInit. Self X, self Y, X and Y, and I initialize like that. And then I have to cpdefs. Why I have cpdefs? Because of the reasons that I have talked about earlier. This reason is also true for methods, for object methods, that you compile two different versions, one when this method is called directly from Cython code, and one when you call it from Cython code. Notice here, before in the Python object, I could directly say what px is. You see, since this is a field, there is no notion of public and private in Python, so you can access the field directly. Here, I compile this. I have the PyRectangle. I can print my area and perimeter. And I try to access a he. But it tells me that the object has no attribute X. This is CDef. So this is internal to the class. I would be able to create methods to access them, but since I don't need to access them, they are not visible outside, since they are defined with CDef here. So self X here refers to this private X of the PyRectangle. So although I can call the perimeter because it's a cpdef function, I cannot call a.x directly. If I define this as cdef, I would not be able to call perimeter either. Any questions?
Yeah, we have a kind of general question from Francesco. So can you mix Numba and Cython? And in general, if one has no legacy Python code to optimize and you know C really well, does it make sense to use Cython instead of Numba or C plus CFFI, C or C with CFFI?
Okay, so there are two aspects to these questions. There is a way to access the C function both using Cython and Numba. What you saw with Numba is that it uses the LLVM, so it does not use the C compiler. It can use it, but you have to tell it, and the syntax is different. When you specify something with JIT, it uses LLVM. It does not use a C compiler. you can wrap a C library with Numba and call it with Numba. But in general, with Cython, you have much more control of what you're doing when you're interacting with the C code. Whenever you see a library that is MPI for Pi, for example, H5Pi, when you see something that is, in general, a package that is the name of the package and a Pi in the end, in most of the cases, it uses Cython to make this intermediate layer between Python and the Cython. So you have, if you know C well, and you already have C libraries that you know are performing well, you have better control with Cython. We will see how you can wrap both C and C++ libraries with Cython. But yes, Numba is good. You can do the wrapping, but it's good from what you saw, for what you saw, that you can compile on the fly using the LLVM code, which you need to hand-tune more Cython to get the same performance. Because as you see, also for parallel and stuff like that, you have to pass the compiler flags and everything. So it always depends what you want to do. So let me proceed a little bit more if we don't have more questions.
Yep, go ahead.
Okay. So here again, I define a SciRectangle, it's the same. And now I define a class which is SciRectangles, which is a collection of rectangles. And here I say list rectangles, cdef. In this case, what I do at the initializer is that I create, based on the number that you give me, a number of random rectangles. And here I use list rectangles. This behaves like a Python list, but it's the compile equivalent, which is optimized by Cython. They offer a list that has the same functionality with Python. It can interoperate with Python lists, but it's the optimized version of a list. So you have, again, the same syntax like you would have in the Python list, append and everything. And here I have a cpdef total area. So I can create 100,000 rectangles and calculate the total area just like that. Now, all this was executed in C, and I was using the optimized list of Cython. The same holds true for other standard Python data structures like dictionaries and tuples. Cython offers the equivalence, but compiled by the Cython developers so that they use the best of Cython while retaining the interoperability with Python and the same syntax. So here, list is a built-in of Cython, like you would have for int, for example, you have list. Now, let's go to what you have asked me before, to work with pointers. So to work with malloc and free in a C code, you would need stdlib. So Cython developers have wrapped the std library of C so that you can use it directly from Cython. And for this, you see that I do from libc stdlib C import malloc free. So this is something between the import syntax that you would use with Python, but you are using to import std CSTD library functions, malloc and free. So here I have a range vector for that I create, which is just a range vector but defined in Cython. And in cdef here, I have the data, which is a pointer to an integer, and I have the size. Here I go in the initializer, and here you see that I do malloc size times size of int. This is what you would do in a native C environment. And this is the syntax that Cython uses for casting. So you have to cast what malloc returns to a pointer of int. Now I can use this for I in range start to end to populate my range vector. And now I can override the typical methods that Python provides, get item to return the I index of my data. But also here, I have to define a destructor, which is the dialog, which is like the delete that you would have in C++, which frees the data and this is called when this object, this SciRange object, SciRange vector object we might have created goes out of scope and it has to be garbage collected. It will call the dialog. So here I create a SciRange vector. Oh, I didn't compile. And you see, I can directly access this. So this is how you can use pointers also, and this can also be used in function declarations and whatever. Questions?
Yep, there's one question from Giordano. For classes, is there any difference between cdef and cpdef? Or is there no difference among them?
No, it's just a syntax like that, cdef. So with classes, you interact with methods. So methods more or less specify what the interaction is. So this is just the syntax, cdef class. Let me go a little faster if there's any other questions.
Go ahead.
Yeah.
10 minutes until the break.
Yeah, so this is a C++ type version of the SciRange vector where we can use the vector from the standard library of C++. The only difference here is that I have to specify that the language is C++ now. So now Cython will use the C++ compiler. And from libcpp, remember before I had to import from libcstdlib. Now there is libcpp.vector, c import vector. So I can use the standard vector that is templated from the C++ library. And cdef vector int, this is how I define that I want a vector of int. This is where the template parameter goes. And you see here that now I have to use the name of the function belonging to the vector, which is pushback, which is the same as is in C++. And I can go on. Here I don't have to specify a dialog because I didn't do malloc and free manually, but I rely on what the vector class has for the allocation. So I don't have to do that. As long as this goes out of scope, the property structure of the vector will be called. So that's another advantage when if you want to wrap C++ standard libraries, or they are already wrapped for you, standard utilities. And for those of the utilities that are not there, you can wrap your own C++ functions or classes, even if they are templates. And you see here, I again define a range vector, but now it was C++. And again here, I show you how you can use it from a function. A cpdef, a vector int for you, just in a sci range. Look what's happening now. As long as I interact with this vector int through Python, Cython has created this equivalent of what a vector is in Python. So in our case, it's a list. If it was a map here, a standard map from the standard C++ library, it would convert it to a Python dictionary. So it makes sure that you can work with it like that. So you see, I can print it directly. I can access it like I would access a list. So that is a very nice thing with Cython, that it has more or less made this binding for you, that you can work seamlessly with containers of the standard C++ library, and you can treat them as their equivalent data structure in Python. And I have here the link for you for the additional STL libraries that they have for C++. They have a lot of things here that they are wrapping, and you can find the one that you are familiar with in C++, but I will show you how you can wrap one that is not already here. So, this was the other one. So, is everything clear up to now? Yes?
Yep, keep going.
Okay, so let's do something else now. I'll go to a terminal and show you some stuff. So I go to Python for HPC, and then I go to Cython and wrapping C. So here is how you would wrap a C code. So I have my primes C function. Here is how it is defined in complete C, native C. So what you have to do in terms of Cython is that you have to define this interface here, the PYX file, PYX, which basically tells how the interaction is going to happen. So this is more or less an is prime that I would call from Python, and it's a cpdef. So I have in the README here how you do this, and you will see. that I have to execute. Let me see if it's like that. Or I don't remember the syntax. It's build text. So now it's compiling for me. You see all the compilation that it is using, and I can call my primes pi, which my primes pi print primes. So in this case, print primes is just importing as a module what Cython has compiled here, and I can call it like a standard Python function. So how does the setup look like? Yes? The setup looks like that. You have to use this Cythonize, which you import from Cython build. So that's one of the reasons that I didn't want to go into more detail into that, because it's more complicated for simple stuff, but it gives you more control if you want to do more complicated things. And let me show you in C++, wrapping C++. So here I have the PXD. Let's see. So here is even more complicated. I have to define in the PXD what I'm going to wrap. And here I use this syntax that you can also import things from standard namespaces of C++. From those of you who are familiar with the C++, this is the syntax. From those of you who have not worked with C++, okay, just have it for reference if you ever want to wrap something. So I tell it that I want to wrap the CPP class, which is Mersenne Twister, and this number here, which is the default random generator of the random engine that C++ uses, C++11. I wrap also the uniform real distribution, and this is a template parameter, as you can see here. So I can wrap this, and now my setup, I don't have a setup here because I will show you the other method of doing it. So I can use this. So I means that I want to do it in place, and -3 is that I want to use the Cython syntax, the Python 3 syntax. So I do that, and now it compiles everything, and I can run like a standard function, the Py calculator. So it asks me for an integer number, and let me give that. For those of you, again, I am saying it that for those of you who are not familiar with C++, just have it. I added this for reference so that you know how to do it. And here you have, if you look at it, you will see that you have a .so that Python has Cython has created for you, which you can import directly from Python and use it as a module. Questions? Questions, anyone?
So no questions at the moment, but we'll have some time to be able to formulate them over lunch.
Yeah. So I'm again saying that Cython has a lot of things that I could not show, but I think that this is a good starting point to at least know what is out there and what is suitable for your situation. I would say that Cython is more for simple things like just adding some type hints and some type declarations and try to optimize your code to run faster. It's okay, but for more complicated things, you have to be familiar with C to start doing useful things. On the other hand, Numba, you don't have to be a C programmer to use it because it doesn't use C. And as you saw it, although you don't have that much control, it's much easier to just decorate your function and make them run faster. And in many cases, in most cases, what Numba will produce for you will be better than what you would do by yourself with C if you're not an experienced programmer in optimizations.